So thank you very much for this invitation. I'm very happy to virtually there. I would enjoy even more to be physically there, but well, maybe one day. So my name is Mathis Plapp, and I am affiliated with the Laboratory of Condensed Matter Physics at École Polytechnique in Palaiseau, just outside of Paris, about 20 kilometers outside of Paris. And I am employed by the CNRS, Centre National de la Recherche Scientifique, which is a national research organization. And otherwise, École Polytechnique is also a university, but I do not teach much there. So my colleagues Hervé Henry and Thomas Philippe are in the same lab as myself, and we are working together since a certain time on phase field methods. And so that's what I'm really a specialist of, phase field modeling. I'm not a specialist of phase change materials or of memory applications. So those specializations come rather from our collaborators, so which are from Grenoble, so which work at CEA, the Atomic Energy Commissions, and at ST Microelectronics. Because so it so happens I'm working on fundamental aspects of phase field modeling, and then we were approached by ST Microelectronics, who is a big electronics company, because they had some difficulties in high performance materials for their memory devices. And they asked us, can you help us? And we said, maybe. And so they then funded the PhD thesis of Raphael Bale. That's why his name is in red. So it was his PhD thesis. And so he should get the main credit for this work, because he was doing the main job. Okay. So as I said, we were approached by ST Microelectronics. So I will start by telling you what it all was about, what help did they want, and what were our objectives. And as you will see, it's a quite complicated problem, and we had to use for the modeling several bricks that we had produced previously, that is several ingredients and model features in some sense that we had all put together. And so I will successively speaking about the grand canonical phase field model that we have developed 10 years ago, about a multi-phase field formalism, about orientation field models, and then in the end, how we put all this together to model the crystallization of GST. And I will tell you in a minute what this is. Okay, so to start with the objectives. So this is about phase change memories. How do phase change memories work? Well, any digital memory, you know, has to store bits, that is, has to encode somehow 0 and 1. And in phase change memories, this is encoded in the state of a material. Because many materials have two different solid states, an amorphous one and a crystalline. And so the information would be, for example, 0 is amorphous and 1 is crystalline. And as many other materials, such phase change materials are in principle glasses. So actually you can control the state in which they end up by the velocity of the quench. So this is symbolized in this graph, where on the y-axis here you have temperature and on the x-axis you have time. If you heat them up by a very short and intense pulse, such that they get over their melting temperature, and then if you quench them down quite rapidly, then they become amorphous. And if, on the contrary, you heat them up a little bit more slowly to a lower peak temperature and then let them cool down more slower, then they have time to crystallize and they will end up in a crystalline state. Now, in the technology that, among others, ST Microelectronics is producing, a memory cell that is 1 bit of this type. So you have a layer of this phase change material, and this is enclosed between 2 electrodes. So one is called the heater electrode and the other one is called the top electrode, because in these devices, the heating is actually produced by current. If you send current pulses through this heater electrode, through the Joule effect, it will produce heat. And if you should send a short and intense current pulse, it will lead to the formation of the amorphous state. And if you send a longer one with a trailing end, then you will crystallize. Okay, and that's how these time scales come. The pulse for making the material amorphous is typically very short, 10 nanoseconds. And the pulse that makes it crystalline is longer, from 100 to 1000 ms. Once it's heated up, they cut the current, and then the heat dissipates away in the material. That controls the velocity of the quench. And the information is read out actually by a small current, because when you apply a voltage, then the two states, the amorphous and the crystalline state, have very different conductivities. So you apply a tension and you read out the current that goes through. In this way, you can read whether the bit is 1 or 0. So that means that PCM materials must have fulfilled certain requirements. So as I have said, if you want to read them out well, they must have a very strong contrast between, in some properties, between the amorphous and the crystalline state. But at the same time, for the memory to be fast, they must to crystallize quite rapidly. And in principle, these are contradictory requirements. Because usually, if you want a strong property contrast, you also need a strong contrast in structure. And if you have a strong contrast in structure, the kinetics of crystallization will be slow. Okay, but there are a few very special materials that combine these two properties, and that's why actually all phase change memories are built from a few materials, very specific ones that might look quite exotic to normal metallurgists. They normally contain chalcogenide atoms, and the most widely used is called GST. It's a mixture of germanium, antimony, and tellurium. And this is used in most commercial PCM memories. So you can buy PCM memory chips. They are already on the market. Okay, and in particular, this ternary mixture has a stoichiometric compound. It's the 225 compound. And despite the fact that this has a quite complex unit cell, in where the atoms are complexly arranged, it crystallizes very rapidly, almost as rapidly as pure substances with spherical atoms. It's quite amazing, but it's like that. And in addition, it has very special electrical properties, because in one of the states is a semiconductor, and in the other state it's a bad conductor. So it has numerous advantageous properties that I could not all explain to you. Okay, but it has one decisive disadvantage. As you know, a glass is not an equilibrium state. So every glass actually would like to crystallize, and it's hindered to do that because everything is just too slow. And so if you heat up the glass sufficiently close to the melting point, eventually it would crystallize. So you can define a crystallization temperature, which is not a thermodynamic concept, which is really depending on how long you want it to take. But if you define that you want to keep your data, say, for 1 year, then the crystallization temperature of normal GST 225 is 150 degrees Celsius. If you heat it up more than that, then it will rapidly crystallize. And this obviously means that you lose the information. Because in the end, everything will be crystalline, and then you will have wiped out everything that was programmed there. And this is annoying, especially for many applications that are envisaged in the automotive sector or in aerospace. When you want to be close to a motor, you would like to have devices that keep working at higher temperatures. And so ST has found a way to do that. They use the GST mixture, but not at the stoichiometric composition. They enrich it with germanium. So they move to the germanium-rich edge of the corner of the phase diagram. This indeed, according to their studies, increases the crystallization. They can get it up to 300 degrees, which is quite. But now when it crystallizes, it doesn't crystallize at the constant composition. There's segregation. When it crystallizes, it rejects germanium into the amorphous phase. And when this rejection is sufficiently strong, that is, when there is enough germanium that is added to the GST, then you can even have the nucleation of a new phase. So this is shown here in the left picture. It's a TEM picture of a thin film that was amorphous in the beginning. It was just baked, so annealed. And you can see here is the color code. Blue is the germanium atoms, green and red are the others. And you see that there are regions where that very rich in germanium. And there are regions where germanium is almost absent, and these correspond to crystals of almost pure germanium with a little bit of dissolved tellurium and antimony, and the reddish region here correspond to the classic GST. And so here to the right, you see a memory point. So you have to imagine this is this mushroom geometry that you see here, okay? So the material that is actually processed during the memory operation is this blue region here. And what you see is after memory operation, actually you have a redistribution of the components. So for example, in this active region that is delimited by the white dashed line approximately, you see that the concentration of germanium has diminished because here blue corresponds to a low concentration, whereas the one of the other components has increased. Clearly, the memory operation changes the composition of the material. And the question is, what is the consequences on this for the memory working? And as you can see here, so this is TEM pictures. So first of all, they are expensive. Second, they are necessarily post-mortem. You can do that when everything is finished, and you often don't know what you have done during the preparation of the samples. So ST wanted to have a sort of tool which would allow them to understand a little bit better what's happening. And if possible, they wanted to have a simulation model that is capable of reproducing these things. Okay. So we said, well, this is very challenging because the model should be able to do numerous things. It should be able to do GST or something that is like GST, so they have the right thermodynamics. It must have three phases: germanium rich, GST, and the amorphous. It should, if possible, also describe the grain structure of the material. And we should be able to couple this to the temperature field that is created by the heating in the memory point. Okay, so this corresponds to the various pieces that I want to tell you about. Probably my talk is far too long, so I will have to skip maybe some parts, but I will try to do my best. Also, this is the first time that I give this talk in this form, so if it's in some parts a bit rough, and if you don't understand something, please do not hesitate to ask. I will try to leave enough room for questions at the end. Okay, so the first part is this grand canonical phase field model, because the first thing is, the first point is we need to be able to simulate the crystallization of a mixture, taking into account the right thermodynamics. So, as I mentioned, I'm a specialist in phase field modeling. So a few general words on phase field modeling. Well, we are dealing with interfaces between different phases. As you all know, interfaces look different when you look at them on different scales. Moves very slowly. So on the macroscopic scale, an interface often looks like a surface of discontinuity between two phases, between here solid and liquid. But obviously, if we look at it on the microscopic level, we know that matter consists of atoms. So the solid is an ordered structure and the liquid is a disordered structure. So we see that these can coexist. And in reality, in physical reality, the order doesn't stop suddenly, but it gradually decreases between the solid and the liquid, such that we have a transition zone, which is the interface. So to which we can thus attribute physical thickness. And if we want to stick to a continuum description, but resolve the finite thickness of the interfaces, this is the mesoscopic scale. This is the scale where the phase field model lives. So here we have a function that can be seen as an order parameter that indicates you whether we are in the solid or in the liquid. And the solid and the liquid correspond to two constant values of this order parameter. And the interface zone is a smooth transition between these two values. Okay. And of course, all of this is not new. And the connection between these various scales has classically been done in this direction by classical statistical mechanics. So the goal of this is always to explain macroscopic phenomena from the microscopic ingredients. But since computers have become powerful, can also go in the other way. You can say, okay, suppose that I know the macroscopic characteristics of a problem. How can I set up a mesoscopic model that simulates this macroscopic problem in an efficient way? And sometimes with managerial words, I call this the bottom-up approach. And the second one, the top-down approach. So top-down approaches, I know what I want, and I make the model do what I want. So this is the more modern take on these diffuse interface models, one on which I have worked quite a bit. And I will try to tell you about several aspects of this. But first, just 10 seconds on the bottom-up approach. So here's again the molecular dynamics picture. And if you look at this, you immediately grasp the fact that you can give a physical sense to a phase field. Because as I have said, the solid is an ordered structure. So for example, here, if you look at the atoms that are neighbors, you will always see them in certain relative angles, because in a ordered structure, all the angles are well defined, whereas in a liquid, your neighbors will appear in various directions and there will be no special values of these angles. So with this, you can microscopically, only from microscopic information, define an order parameter that will indicate you whether you are in the solid or in the liquid. You can also use things like density functional theory. When you average density over this direction, for example, in the solid, you have alternation of dense and empty planes, whereas in the liquid, density is homogeneous. So both of these tools can give you an order parameter. And if you want to fit this into a continuum description, this is a very standard procedure. In the continuum description, you start from a free energy functional. So your free energy, the total free energy of your interface, is a volume integral over an integrand that has two terms. That is one. The second one here is a double well potential, which has this shape here. It's a double well potential for the order parameter, and the two minima precisely give you the constant values of this order parameter that correspond to the two phases. And the first term is a gradient square term. This arises from the interaction between the different parts of the systems and is always there as soon as you have interactions. Now, this type of free energy functional is usually called a Ginzburg-Landau free energy functional, and is called as such after the 40s, because Ginzburg and Landau developed the theory of superconductivity, but it's actually much older than that. The first one, to my knowledge, who formulated such a theory was van der Waals, but nevertheless, so this is known as the van der Waals with his theory of the liquid-gas interface, but nevertheless, this is called the Ginzburg-Landau functional, deservedly so, because Landau showed that you can apply this to all phase transitions. So it's quite universal, and it contains two coefficients here, which I have called K and H. And these can illustrate the difference between the bottom-up and the top-down approach. So in the bottom-up approach, of course, you take some microscopic model with some interaction potentials, and the goal of your StatMech enterprise is to calculate the coefficients K and H. Okay, so this is the classic goal of mean field theories and so on. But you can also use them in a different way, because we can start from very simple dimensional analysis and go about and see that F here is a free energy, so it's in joules. This is a volume integral. If F here is a dimensionless function, then my coefficient H is dimension of energy per unit volume. Okay. In the other term here, there is a gradient squared, which brings a length squared in. So the dimension of K is energy per unit length. That means that if you take the ratio of these two coefficients, you get a length. If you take the square root, a length that I will call W. And if you take the square root of the product of the two, you get energy per unit area. And so these are two physically interesting properties of the interface, because the W here is the width of the transition zone of the interface. And the gamma here is the surface energy, because this has the dimension of energy per unit area. And you can also very nicely relate this to the coefficient A, because H is the height of the potential barrier between the states. This potential barrier contributes over a layer of thickness W. So the surface energy due to this, the presence of the interface must be proportional to the product of H and W. And if you feed the premier relation in, you see that all of this is congruent. Okay, so you get very simple scaling relations that are universally valid between the two coefficients that appear in this functional and the surface energy and the interface width. That means in the top-down approach, if you know the surface energy because somebody has measured it, and if you have an idea either what the physical interface thickness is or what interface thickness you would like to produce to solve a mathematical problem, then you know how you have to solve these coefficients, how you have to choose these coefficients KMH. Okay, now this is an equilibrium interface, and these are equilibrium properties. Now, if you want to do growth, we have to couple this to thermodynamics in order to make the interface move. And this has actually been done right from the start for a pure substance. So in a pure substance, for example, if I think about the solid-liquid transition, then the density is approximately the same between solid and liquid. Assume that it is the same, and then the only variable that is relevant for a pure substance is the temperature. And so the thermodynamic part of the free energy, I can write this as the volume integral of a free energy density. And well, I know that I have two phases, solid and liquid. So my thermodynamic part, a free energy density, it's the free energy density of the solid if I'm in the solid, and the free energy density of the liquid if I'm in the liquid. And so my function G of the phase field, this is just a weight function that is 0 in the liquid and 1 in the solid. Okay, and since the order parameter varies smoothly, this weight function also varies smoothly through the interface. But actually, this is nothing but a sort of a smeared out representation of the macroscopic free energy. Because how would you calculate a macroscopic free energy? Well, you would take the free energy of the solid, the free energy of the liquid, and add the interfacial free energy. So interfacial free energy is this, and this here is the combined solid and liquid free energy. Because if you think that the GS here would be the heaviside function or the indicator function of the solid, then this integral here would just reduce to this one. Okay, and then if you say, okay, I'm interested in temperatures close to the melting point, then I can do a Taylor expansion of this free energy density around the melting point. So this is just a fourth order expansion in the temperature. And I can use that this coefficient is nothing but the entropy density. And then I can use, so here the index nu means solid or liquid. And I can use that actually for a pure substance, the free energies are the same at the melting point. That means that my thermodynamic part of the free energy is just a constant plus a contribution that is proportional to the difference of the temperature from the melting point, and that contains this interpolation function, this weight function G. And the coefficient contains the difference in entropy density between the solid and the liquid, and this is nothing but the latent heat. And this gives you another interpretation of this weight function, because it is often called a tilting function. Because, as I've said, when the two phases are in equilibrium, this is the black line, then the two wells are of equal depth. If I add the thermodynamic temperature energy in this form here, if I'm above the melting temperature, well, then the favored phase is the liquid. So the well is tilted to one side. And if I'm below the melting temperature, then the favored phase is the solid, and then I'm tilted in the other way. Okay. So everything works fine for the thermodynamic coupling. The temperature just tilts me the double well in one way or in the other, which will make the interface go one way or the other. So in order to get the evolution equation, I can just use two things. So the order parameter adjusts itself to the local thermodynamic conditions. So it will also always tend to the state that locally minimizes the free energy. So this symbol here is the variational derivative of the free energy with respect to the order parameter. And this is nothing but a relaxation equation it always goes downhill to find its local minimum with a kinetic coefficient that is called the phase field mobility. Now for the temperature, things are slightly more complicated, but not much. So for this, I have to use that actually the temperature changes because heat is exchanged. And so heat is energy. And for this, I need to use, on the one hand, that I have a conservation law for the internal energy. So if the local energy changes, it's because I have a heat current. So kappa here is the heat conductivity. Delta T is the temperature gradient. So this is Fourier law of heat conduction. This is a divergence. So this is nothing but a heat conservation equation. And on the other side, I can use that I have my first law of thermodynamics. If my density is constant, then the change in internal energy is just TdS. And the entropy actually depends on the temperature and on the phase field. So I use the chain rule and I get that I can express the variation of entropy in terms of temperature and phase field. And now if I use various thermodynamic identities, namely this identity for the specific T and this decomposition of the heat conductivity in terms of the heat diffusivity, I get an equation for the temperature, which has a diffusive part and a heat source part. The heat source is active only in the interfaces where the phase field changes and is proportional to the latent heat. This was a sort of classic exposition for a phase field model for the pure substances. Now, I have said we need a phase field model for a mixture. And here is where thinking can become somewhat more non-conventional. So suppose that we have a mixture that crystallizes. So this is like isothermal solidification of an alloy. And if I make again the approximation of constant density and I neglect fluid flow, then the transport of solid atoms is diffusive. This is the only transport phenomenon that I need to take into account. I have got a solid current that is now driven by the gradient in chemical potential. And I have a balance law for the local composition, which is the divergence of the current. So this is nothing but mass conservation. And here, this is the classical thermodynamic law of chemical diffusion. It's the equivalent of Fourier's law for heat conduction. Okay. And now suppose that I want to write down a phase field model. And now instead of on the temperature, the free energy densities of the solid and the liquid will depend on the composition. And so the variables of my functional f will be phi and c. And so for phi, I will write the same relaxation equation as before. But for c, I need to take into account this conservation law. So I take the divergence, I write the expression for the current, and the only thing I do, I will replace mu here by the local functional derivative of f with respect to c. And this is exactly how the first phase field models for Alloy solidification were written. But now let's consider the thermodynamic driving force. So if I want to do the same thing as before, that is, I say my thermodynamic part of the free energy is now a superposition of the solid free energy and the liquid free energy with the same weight function as before. I run into trouble. Why? Because this time, well, as you know, in a mixture, if a solid and a liquid coexist, they do not have the same composition. So the composition is different in the solid and in the liquid. And in addition, the free energy density is also different in the solid because they are not the same. And why they are not the same? Well, you might remember how you construct a phase diagram of a mixture. You use, of a binary mixture, you use what is called the common tangent constructions. Is if you have a free energy function for the solid and for the liquid, well, you will have to find the common tangent, that is the tangent that touches both curves in a point. And then the compositions of solid and liquid will be these touching points. And in more thermodynamic conditions, this will correspond to the condition that the chemical potential has to be equal in both phases. And this combination F minus mu C has to be the same in both phases. So this can be called the grand potential. It's not strictly the grand potential, but it's something that is really analogous to the grand potential. And now you see where the problem is. If I do not have the same composition in the solid and the liquid, then of course, through the interface, my composition has to vary. So the composition goes all the way from CS to Cl. Now, if I apply this interpolation here, first of all here, I apply the free energy functions of the solid and of the liquid with the same composition, which just doesn't make much sense because coexistence solids and liquid don't have the same. And also I will use these free energy functions for value of the concentrations that will be far from any equilibrium composition, which means that all of this will go into the calculation of the thermodynamic free energy. And in addition, you can see from this curve that the two free energy densities are not the same. So I will get a driving force even at equilibrium, or in other words, the two contributions F thermodynamic and F interfaces in this formulation are not properly separated. Okay, so how can this be solved? I have myself contributed to a first solution that concerns a special model that is just valid for dilute alloys. For this, you have to do some more complicated interpolation. It has become quite popular, but it's not a general solution. Okay, then there was this approach put forward by the people from Access in Germany and also quite famous by Kim and Suzuki. They said, okay, if solid and liquid have not the same composition, then let's introduce two composition fields, one for the solid and one for the liquid. Okay, then we can properly write down the interpolation of the free energy with two different concentrations. And the true concentration, we will also get it as an interpolation. But of course, then you have sort of introduced one additional degree of freedom. You need to eliminate this. And you can do this by either relating directly the solid and liquid compositions. This is the dilute alloy approximation, or in the general case, you have to require that the two chemical potentials in liquid and solid are the same. Okay? This works perfectly fine. The disadvantage is that you have a system of equations to solve at each space point, so it's quite heavy. And so the new ideas that we put forward from 10 years ago is that actually all this is far easier to formulate in the grand potential function. So you can deduce this in some sense from a little table that gives the analogies between a pure substance and alloy. You know that in both cases, I have a transport phenomenon. In the pure substance, it's heat. In the alloy, it's solid. There's a conjugate, thermodynamically conjugate thermodynamic, very intensive variable, which is the temperature of the substance. It's the chemical potential for the alloy. Now, if you continue this table, you see that you can always have several thermodynamic potentials that are all equivalent, but they are different whether you express them in the extensive or in the intensive variable. So for a pure substance, if you want to use the energy, which is the extensive variable, the heat, then your potential is the entropy. If you want to use temperature, then it's the free energy. And in the alloy case, well, the extensive variable here is the solute concentration. So for this, the appropriate thermodynamic potential is indeed the free energy. But if you want to use the intensive variable that would be analogous to the temperature, then you should not use the energy, you should use the grand potential. Okay. And for me, I think it's quite obvious why people wrote from the start phase field models for pure substance in temperature and for alloys in composition, because that's the two things that you can easily measure. But thermodynamically, they are not equivalent. The equivalent of the temperature is the chemical potential and not the composition. Okay, so let's see how this goes. Let's take the grand potential. So let's take the same stance that we did for the pure substance in the free energy. We separate the total thermodynamic potential, which is the grand potential, in an interfacial and a thermodynamic part. And for the thermodynamic part, we take a superposition between solid and liquid. Now, here, these functions omega of mu that appear here are the Legendre transforms of the free energy. So the free energy is a function of composition. The Legendre transform, you calculate F minus mu C, and then you change variables from C to mu. So the resulting omega is a function only of the chemical potential. But you have to understand it in this sense. You take the free energy function, that is a function of C, but then you express C as a function of mu, and in this way, this becomes a function of mu. So this is the classical mathematical trick of the Legendre transform. And if then you write down the equation of motion for the phase field, explicitly you get here the interfacial terms as before. And now here in the driving force, you get the difference between omega s and omega l. And precisely, if you remember the double tangent construction, you see that this is the omega s and this is the omega l, and in the equilibrium, they are identical. That means in equilibrium, the driving force is zero, which is just the same thing as happened for the pure substance model with the temperature. So it's nice because in this way, we have achieved a complete decoupling between bulk and interface part. And we can fix the energetic parameter without hesitation. Now, for the equations of motion, we have to do the same thing as before, but now for the concentration. The concentration is now a dependent variable. It depends on the phase field, on the chemical potential. So if I take the variation of the composition, this is now a function of the variations of the phase field and of the chemical potential. So this derivative here, I calculate chi. It's actually a generalized susceptibility. And I write down again now the equation for the composition. Here's the conservation law that I started from. Now I divide this equation here by dt, and I get that chi times dt mu. I can express this as dc by dt, for which I use the conservation law. And I explicit the derivative dc of d phi, which gives me this. And so you see that I have arrived at an equation which is completely equivalent to my temperature equation, but now for the chemical potential. And as I stress again, chemical potential and temperature are thermodynamically equivalent variables. There is a part that is diffusive and there's a source term. And the role of the latent heat here, which is the difference between entropies of the two states, is now here played by the difference in composition. So it's again the jump of a quantity through the interface that appears here. So everything is totally equivalent. And so now, if I want to use this in practice, how do I do that? Well, the starting point should still be free energy functions that I can obtain, for example, from a CalFat database. Then I need to perform the Legendre transforms, and it is generally advantageous to use what I call a mixed formulation. That is, I keep both C and mu, and then I use mu to calculate the driving forces for phase motion and the solid currents. But I keep C for updating without any errors the mass conservation law, which ensures that I get a good mass conservation. Okay, and I also want to mention here, I have done the example for pedagogical reasons for a binary mixture, but this can be extended in quite straightforward way to multi-component mixtures. So this was done soon by, after our first publication by these persons, Abik Chowdhury and Britta Nestler in Karlsruhe. And their group has since then used a lot this formalism in multi-component systems. So I quite believe what they do. Okay, well, I think I have to drastically accelerate if I don't want to go over time a lot. So multi-phase field formalism, this is just to say if I have several phases, you need several phase fields. So instead of a double well, if I have 3 phases, I need a triple well. What I need to be careful about is what is the structure of the interfaces, because what I would like to, if I have 3 phases, that the interface between any 2 phases is clean. That is that there is no adsorption of the 3rd phase. If I do that not carefully, I will get this instead. That is an interface with a third phase adsorbed. So you have to carefully choose all the interpolation functions in your model in order to achieve this. This we can do. So we have explicitly done this a long time ago for eutectic solidification. So the functions are a little bit complicated, but they are all given in the relevant publications and we can just use them. And this was all benchmarked, so we can really believe the model. So then polycrystals. So this is the part on orientation field models. Well, if I want to do polycrystals, I can do this in two ways. Either I can introduce one phase field for each grain. Certainly feasible. It's a generalization of the multi-phase field model, but it's heavy because I need to handle a large number of fields. I also need to specify a large number of interaction between fields. So the alternative idea is to use an orientation field model. That is where I give as two variables the sort of local crystallinity or the local order parameter of my material, and as a second variable the local orientation of the unit cell. So to give you an idea how this should look like, here is a density functional calculation of a grain boundary. So you see two hexagonal 2D crystals on the two sides that have a different orientation, and in between you have a grain boundary. And as you can see from the color code, and it is easy to see, the order is more pronounced within the grains than in the grain boundaries, clearly because the positions are disordered. So if I define my order parameter, which is still the phase field, well, then it has one value in the grains and it has a dip in the grain boundary. And the orientation field, on the other hand, it has to have one constant value in one grain, one constant value in the other grain, and have a localized variation of the orientation inside the grain boundary. Now, to construct such model is actually not entirely trivial. And I had prepared some slides on that, but I will skip them because in the end, the only thing that is important is that it works. So here is a simulation of grain coarsening with an orientation field model. So what you see here is the phase field. The first picture is a lot of different nuclei with different orientations that all grow, they impinge, and then here in the other pictures, you see in the grain boundary networks portions with time. And you see some grain boundaries more pronounced than others. That's the high angle grain boundaries. Because in high angle grain boundaries, the dip in order is more pronounced than in low angle boundaries. Okay, so let's see how I can apply all this to the crystallization of GST. Well, we need to do a lot of approximations. The first thing is, instead of doing the full ternary system, we do a pseudobinary approximation. So we have our system live on this red segment in the general ternary GST. We have a single concentration variable that is on that segment between the stoichiometric GST phase and pure germanium. This is justified by the fact that in all the concentration maps, antimony and tellurium are always strongly correlated. Then we need to have an idea of the phase diagram. So here is a two-dimensional cut with axis temperature and composition. It's not exactly the cut what we need, but still we can see that we have here is pure germanium. And we have a solubility with a liquidus that goes down here. Here's the pure GST phase. And if we enrich this in germanium, we have also a liquidus that goes down the other direction. So this is a phase diagram of eutectic type. You also can see that here's a lot of different stoichiometric phases actually in the TEM data from our partners at ST Microelectronics. They say that they only can see the stoichiometric GST phase. So we have limited ourselves to three phases, namely germanium, GST stoichiometric, and the amorphous phase. So here's the phase diagram that we have obtained. It's of the eutectic type. We have fitted this to various data available from the literature, the liquidus slopes, the melting temperatures, latent heat, and so on. This is really quite in the spirit of Calfat. Okay, and then we had also to calibrate the phase field mobility. This is always a difficult subject, but here we had some data on the crystallization speed of pure GST, which were published in this very nice paper. And it has the characteristic sort of bell-shaped curve. Here, the crystallization speed increases because the driving force goes up. And then here it goes down again because the mobility of the atoms goes drastically down because we are approaching the glass temperature. And so we have sort of sampled these data and used this to express our phase field mobility as a function of temperature. Here's our collection of equations, which is a combination of everything that I have presented: a grand potential free energy, the evolution, the multi-phase field evolution equation for the phase fields, equations for the orientation field, and the equation for the solid principle. And now we have done two types of simulations, and I will be finished in just 4 to 5 minutes. The first is the annealing of an amorphous film. So this is the considered configuration. We have a thin layer of the as deposited film, and then this is heated up until crystallization sets in. And from experimental observations, we know that the germanium phase nucleates first. So this we will use as initial condition. And then when the germanium grains grow, the matrix gets more and more depleted in germanium until at some point the GST phase can nucleate. And this we handle by using classical nucleation theory. And when the probability of nucleating a GST is high enough, we put nuclei of the GST. So here's the sort of initial state. We have various grains of the germanium phase with different orientations. So all the different hues of red and pink are different orientations of this phase. Then the phase grows until here, the first bluish thing is the first grain of the GST phase. Then we have nucleation of other grains. So you see that they rapidly engulf the germanium grains and form grain boundaries. Then the amorphous phase is completely consumed, and we have a polycrystalline polyphase material. And this then coarsens with time. So I like the difference between these two pictures because you can see that there are several coarsening mechanisms at play. First of all, there's usual Ostwald ripening, meaning the small the small domains here of germanium will evaporate and the atoms will diffuse on the bigger ones. For example, this one here will disappear. But there's also another mechanism here. You have two grains separated by a grain boundary. You can see that the grain boundary is mobile, and so the smaller grains will be eliminated by the migration of a grain. So we capture a lot of different coarsening mechanisms in this complex material. And here's our final picture, and here's a qualitative comparison to the TM picture. Unfortunately, it's rotated by 90 degrees, so here the film is vertical, whereas in our picture it's horizontal. You cannot say much more than, well, we have a polycrystalline two-phase material because there's too many approximations to have a quantitative description. We see that our germanium crystals are smaller than the ones in the experiments, but it's also because our simulation was not able to do the same duration of annealing as the experiments. And you can also see that obviously we are missing some things because the structure in the experiment seems to be much more anisotropic than in our simulations. So, which is quite natural since we didn't put any anisotropy anywhere. Okay, so this is a sort of isothermal annealing. Now, here comes the simulation of memory operation. So for this, we combined our phase field model with a macroscopic electrothermal solver. So this is a program that solves the combined electrical and thermal problem and calculates the time-dependent thermal field in a memory contact as a function of time. So the white frame here, this is the active cell. So this is our simulation cell for the phase field model. Here below is this heater electrode, which will emit heat when it is traversed by a current. And so here the colorful shades are the temperature field. And so we sample this and we feed this as an input in our phase field model. And so for this one, I have a movie that will play there now. Okay, so the black is the amorphous phase, and when the system heats up, there is a melt pool that forms in the material. We take as an initial state the annealed film that we have produced in the previous simulation, and now the temperature goes down again, and you see that the system crystallizes, and at the end, the amorphous phase has disappeared. I'll play it once more. Because you can see that here the germanium grains grow first quite a bit, then they are all engulfed. So there is a portion of the sample where there's only GST phase. And then at the very end, the germanium phase appears anew in these trijunction points. This is something that we do not yet fully understand, but. And here is a somewhat more quantitative analysis where we have averaged the composition field over these annuli that are colored in different colors here. And we can compare our composition from before in green and after the operation. And we can see that indeed some of the germanium has been expelled from the active region, which is here, toward the external regions, which is here. We have sort of a wall of germanium here outside of the active region and the depletion inside. Okay. And with this, I'm in the end. So we have been able to formulate a model that can account for the principal effects or during the memory operation in this quite complicated material. And we have coupled it with an electrothermal solver, and we can get at least a mock-up picture of these memory operations. And as a perspective, well, this is a very approximate model, but Raphael had to sort of cut his way through the jungle, and he has gone to the other side. I think that this is a real achievement. And now we can sort of enlarge the first path that we have frayed in improving on the many approximations. So we need a better thermodynamic assessment. We need a better input for the kinetic data. We need better numerical schemes. And it would be nice to have a true two-way coupling between the phase field and the electrothermal solvers, because the different phases do not have the same properties. So the electric current will certainly also be influenced by the microstructure. And ST Microelectronics was sufficiently happy with our results that they fund us a second PhD thesis to work along these lines. And with this, I thank you for your attention, and I'll take all your questions.
Thank you very much. It was a very exciting talk, very interesting. So yeah, floor is Peter is first to ask the question. Go on, Peter.
No, sorry, I just wanted to applaud for the, for the lecture, but I can ask a question. I wanted to ask a question anyway, so I can ask it now as the first person. So, I mean, really impressive, the modeling that you have done. I mean, I was when do you really can get out of this type of modeling? Mm-hmm. when you describe like the formation of this microstructure, do you try to understand the factors that might influence at the end the different structures that you might get? So what is influencing the formation, or do you really are interested in providing a quantitative description? Because you said at several points, we can't really yet have a quantitative result, but do you really want to have this at the end, or do you try more to understand what happens when this material forms?
Well, let's say if we want to have a real quantitative model, there is work for at least 20 years ahead. So that's not our goal. Of course, even in its current state, the model can be used to do some parametric studies. Okay. So for example, as I have said, this is what I have shown is the set pulse. That is the pulse that makes the material amorphous. Now we have also done simulations. No, this is the pulse that makes the material crystallize. Okay. We have also done simulations for the other pulse, which makes the material amorphous. So the only difference there is that the current pulse has a different shape. And what happens is that the temperature goes down so fast that the phase field mobility goes down so fast that the interface at some point just stops. and the core of the active zone remains amorphous. Okay, so the model can correctly capture the transition between the amorphization and the crystallization dynamics. And that means you can study the influence of the current pulse. And that's something that interests the engineers, because in principle, you could vary the composition and then you could play around with the current pulse and see what the model predicts. And even though you will not get hard numbers, you will be able to further understand some trends that you can then try to confirm with experiments, or you can try on the other way around to explain some of the trends that are observed in experiments with the outcome of the model.
Okay.
Okay, thank you.
Okay, thank you.
Yeah, Ross, please.
So obviously your simulation is non-isothermal in both space and time. So then I was just wanting to ask, is there any reason, because obviously, like, if you're aware of kind of Penrose and Fife, that they proposed that an entropy functional should be used for, you know, a non-isothermal model with multiple phases. Is there any reason that you've not then basically used an entropy functional and then taken the Legendre transformation, just like you have with the grand potential, to get something that's like the grand potential, but then doesn't have temperature as a natural variable?
Well, this is just this is one of the points of this list. Actually,
Right.
For the pure substance, it was the other way around. For the pure substance, people first formulated the model in a free energy functional with temperature as a variable. Okay? Penrose and Fife later pointed out correctly that it would maybe more fundamentally correct to use an entropy functional with the energy as a variable. Now, you know that in equilibrium, there is an equivalence between all these ensembles. Even out of equilibrium, you can write all these models in the different things, but in the different potentials, but the difference really comes at the interface. Because this is something that Penrose and Fife did not necessarily appreciate, because at the time the discussion was not that advanced. But they will have with the entropy functional the same problem for a pure substance than you have with the free energy functional for an alloy, because the internal energy density is different in liquid and solid. And this is the equivalent of the composition. It's the same thing, because the latent heat indeed is just the difference between the internal energy densities between the liquid and the solid. So if you want to use the internal energy density as a variable, this variable varies through the interface, and it will be different in the liquid and the solid. So liquid and solid do not coexist at the same energy density. And in this sense, it's not natural to use the energy density as a variable inside the interface. Okay, so in some sense, the passage from the entropy functional of Penrose and Fife to the free energy functional for the pure substance is just the same as the passage from the free energy to the grand potential for the alloy. Only that it was never necessary to do that, because people started out with the free energy functional. Whereas for the alloys, people did not start out with the grand potential. They started out with the free energy.
Yeah. So you don't see any reason, because I mean, I would just then say, well, then you kind of use your interpolation functions, your switching functions, to then interpolate the different internal energies between the phases.
Yeah, absolutely. That's what's inherent in the free energy function formulation. Well, I didn't have that on my slides, but if you calculate the derivative of the free energy with respect to temperature, you will naturally see that you interpolate the entropies. Liquid and solid, which is just what you need. And then you can also show that you naturally interpolate the internal energies. Now, there's also one difference that makes life much easier in the thermal model. It's usually that the internal energy and the temperature are linearly related. Or in other words, the specific heat is almost a constant.
Yeah.
Because the relation between chemical potential and composition is normally quite nonlinear.
Yeah. Well, I was going to say that I mean, well, that was one of the things I was going to say is you can probably also derive it much like you derive your susceptibility with the specific heat, because then it is the partial derivative with respect to whatever it is. It would probably be whatever your natural variable ends up, because you'll probably have, well, you'll end up with something that's like your chemical potential divided by the temperature, which then becomes problematic. But it was just in case you could see any thermodynamic problems with that before going ahead and doing it.
No. There is no thermodynamic problems with that.
Cool. Thank you very much.
Thank you. There are any more questions? Andrew, please.
Just a quick question. So a lot of people in the center are involved on the numeric side as well. And you mentioned you got an explicit solver. I think I saw that, and you use finite difference schemes.
Yes.
And then you were coupling on the other fields with ComSol. Have you considered doing a fully integrated, say, finite element solver for everything?
We are just thinking about this now. Rather, where it was, yes, here, yes. So my stance is always, I'm interested really in the model development and in the theory behind it. So that's where my main work goes into. I'm not a numerical analyst. So I do not want to spend long times on complicated and sophisticated schemes. But if somebody wants to collaborate and do that side of the work, I'll be happy. I will not insist on an explicit scheme because I know that it's inefficient, and one should do better, because if you do that for big simulations, it's a waste of resources, which you shouldn't do, because you will spend a lot of calculation time on things that you can do more efficiently. So obviously, yes. On top of once now the model is developed, I think we should work on making the numerics more efficient. Yes.
So if you are in search of the numerical tool, this is what we are doing.
Okay, very good.
Multi-field problems are not a big issue for us.
Okay.
And then maybe we could help.
So you're doing finite element.
Yeah, we develop a generic code which is called MOFEM.
Okay.
And then for some time, so 7 years, it's still young for finite element, but we can solve the this is the kind of the parabolic, nonlinear parabolic coupled equation. We are quite good with that, and in fact, with Andrew, we're working on as well on the explicit implicit schemes, that you have two processes. One is quick, one is fast. One is quick and one is slow, so we can, for part of the equations, we can apply explicit solver, for another part implicit, and we can
we have explored a little bit of free fem plus. You know, free fem.
Yeah, we know that free fem plus plus. Yeah, very good.
We have played around a little bit with that. Raphael has played around with it for about half a year, I think. But then, because the equations were still in the making, it was not the right moment to try to do the numerical optimization. I'll be happy to explore such.
So our code you can check. It's called MOFEM. So MOFEM. If you put it in Google, you will be asked right on top of it.
So that's an open source package, or
open source? We develop it so mostly partially for industrial applications, but I think that we can help with that.
Okay, very good.
I don't in those particular equations, I don't see any difficulty, which it will be easy to discretize.
I will discuss that with our new PhD student, because they wanted to prospect for different things. So
yeah, I think, I mean, Ross and I were been playing with Moose. That was the one code. So Ross is more the Moose expert, but I think from the sort of general functionality, something like, I would imagine 3-dimensional problems also of interest. I mean, everything you show is 2-dimensional. You talk about triple junctions,
absolutely,
but the real story must be far more complex if you wanted to capture that, and you'd need adaptivity as well. You need to resolve areas around interfaces adaptively.
In fact, it's amazing because this is 2D model, but you get this something which makes you can make some use from 2D, yeah. But
yeah,
theoretically it should be completely in 3D looks completely different.
Yes.
So how long it takes you to run such analysis at the moment?
I think Raphael, it took him, so like the movie that I have shown, I think this run for almost a week.
Mm-hmm. So, but I understand that you're doing one step with your code, then you transfer the data to console.
No. Actually, the console calculation is much quicker. So it's done separately, and then the data are stored. So the temperature just in a big file.
So then,
yeah.
Because I thought that there is some coupling between the
no, that's what I say. For the moment, it's a one-way coupling. So it's we calculate the temperature field, and then we give this as input to the phase field. Obviously, the real challenge is to have a two-way coupling. That is to feed back the information on the morphology in the electrothermal solver. Right?
Mm-hmm.
But this is then the usual multi-physics, multi-scale problem that it becomes very stiff because the transport coefficients for heat and for solid are very different. So you have a sort of
yes, that's why you the explicit implicit schemes.
Yes, that's why we need real
direct application for that case.
Absolutely.
Yeah. Thank you very much.
Thank you,
everyone.
Thank you, Mathis.
Have a good evening and have a good weekend.
Thank you.
Yes, you do.
too.
Thank you very much.
Thanks a lot. It was great.